So, Adriel, Marita, any doubt from the last lecture?
No, sir.
Okay, so yesterday we have finished the thermal properties. We discussed thermal properties and we have discussed a part of thermodynamics also. We discussed up to internal energy. Okay, now we'll start with the work. So, what is the formula of work done in mechanics, Adriel?
The force and displacement.
Yeah, in the mechanics, the work done is the dot product of force and displacement. If your force is constant and if your force is variable, then it's integral. But when you come to thermodynamics, the work done is it's integral of pressure into change in volume, and the limit is from V1 to V2. This is when the pressure is variable. If the pressure is constant, instead of integrating, what you can do is work done is just pressure into dV. The integration of dV is V1 to V2. Work done is PV2 minus P1, or work done is pressure into change in volume. So you will be using these two relations. If your pressure is variable, then this is integral of PdV. But if your pressure is constant, it's just pressure multiplied by change in. These are the two expressions for work. This is for variable pressure and this is for constant pressure. Then we have some conventions in pressure. Like if your gas is expanding. So if gas is expanding, that means volume is increasing. Volume is increasing, that means change in volume is positive. Change in volume is positive, so your work done is positive. If the gas is compressing, means the volume is decreasing. Volume is decreasing, that means change will be negative. If change is negative, then work done will be negative. So these are the relations for calculating work done in thermodynamics. Just note it down. Krishna, yesterday we discussed thermal properties like surface tension, specific heat and latent heat, and we started thermodynamics. So we just have discussed some definitions of thermodynamics in the last class. The major part will continue from today, from this lecture.
Okay, sir.
So you can note it down from here, work done, the definition of work. Or just write these two expressions. If you have a variable pressure, then it's integral of PdV. If you have a constant pressure, then it's P into delta. Okay, did you get the admit card for JEE Mains? Adriel, Krishna, Marita, did you get the admit card?
I haven't checked yet, sir.
No, so I think I didn't.
Okay, just whenever you get the admit card, just inform me about the date of your exam. Although we have planned up to 4th April, but if your exam date is on 7th or 8th or 9th, then we can plan board classes. This is my contact number. You can just WhatsApp me the exam. I hope you all have all have written. This is for the variable pressure and this is for the constant pressure. And this is work done for a for expansion, work done is positive. For compression, you work done. So Written? Can I scroll it?
Just a minute, sir.
Tell me once you have written.
Done, sir.
Okay. In thermodynamics, three graphs are very important. One is pressure versus volume, another is pressure versus temperature, another is temperature versus volume. These three graphs are very, very important for thermodynamics. PV graph is also known as indicator diagram. Indicator is the instrument through which we experimentally measure pressure and volume. That's why this is also known as indicator diagram. So if this is pressure versus volume graph, see, if you look at this graph, or increasing volume, what is happening with pressure, Krishna?
Decreasing.
Pressure is decreasing. So through this graph also, you can calculate work done. Basically, the area under this graph will give work done. So if your volume is increasing, this is expansion, then this area will be positive. Here, you can see this arrow is to the left, means volume is decreasing, its compression, your area will be negative, the work will be negative. So you can calculate work done through area under PV curve also. There is one more thing here, which is cyclic process. Cyclic process means process in which system regain its original configuration. Original configuration means, let's say you start with a gas. Initial pressure of the gas is 180. Initial temperature of the gas is 300 Kelvin. Okay. You take this gas through series of changes, means you change its pressure to 2 atm, temperature to 350, then its pressure will become 3 atm, temperature becomes 400, then its pressure becomes 2.5, temperature becomes 325, and finally it comes to its initial state. Means the final pressure becomes 1 atm and final temperature becomes 300. This type of process in which system returns to its initial state is known as cycle. So for cyclic process, this is the PV diagram. So PV diagram is basically a cycle. So in cyclic process, if you want to calculate work done in a cyclic process, here PV diagram is a closed loop. Then work done is area enclosed by the loop. So for work done, you will be using this area. This area enclosed by the loop is work done. This area enclosed by the loop is work done. You will not be using area under the graph. You will not be using area under the graph here. You will be using area enclosed by the loop. So there's a difference here and here. Here it's area under the graph. Here it's area enclosed by the loop is what. And if your loop is clockwise loop means expansion is more than compression. So work done will be positive. And if your loop is anti-clockwise, then your work done is negative. And one more thing, can you, Adriel, guess what is change in internal energy in a cyclic process? We discussed this thing yesterday also. What is change in internal energy in a cyclic process, Adriel?
None,
Why not?
because potential energy.
Because internal energy depends only over initial and final position, right?
Right.
So in cyclic process, initial and final are same. So initial and final internal energy will be same, and there won't be any change in internal energy. That's important. This is important when you use first law of thermodynamics. Just note it down, please. Can I scroll it?
Yes, sir.
Yes, Krishna, written. Can I scroll it?
Just a minute, sir.
Tell me once you have it.
Done, sir.
Okay. What question on it, but okay. So the next is first law of thermodynamics. First law of thermodynamics is nothing but the conservation of energy. It simply says if you have a system, that system may be an ideal gas. If you provide some energy to the system, then gas can utilize that energy into two ways. That energy can either change its internal energy, or due to that energy, it can expand or it can compress, means gas can do some work. So the heat energy provided to a gas can be utilized in two forms, either in the change in internal energy or either in the form of work. So you can say that delta Q is delta U plus delta W. So delta Q is the heat given. Delta U is the change in internal energy. Delta W is the work. So there are certain sign conventions. If your system absorb heat, then delta Q is positive. If your system reject heat, then your delta Q is negative. If temperature increases, then internal energy is positive. Temperature decreases, then internal energy is negative. In expansion, work done is positive. In compression, you work done is negative. Not at all. Do two questions on this concept. Tell me once you have it. Yes, written.
Done, sir.
So for first law of thermodynamics to apply, the pressure should be a constant.
No. I just wrote here that if pressure is constant, then work done is V delta V. If pressure is not constant, then work done will be integral of V. It's applicable in all cases. So basically, two type of questions can come into the first law of thermodynamics. One is this. No need to write the question in the PYQ of NEET of thermodynamics. This is the first question. NEET PYQ. Let's solve this question together. Huh? We'll save some time. Then you will realize why I was saying that in entrances, usually they mix thermal. So the question says you have 1 gram of water. The volume of water is 1 centimeter cube at 100 degrees Celsius. What is the density of water, Krishna?
1 gram per centimeter cube.
So density of water is 1 gram per centimeter cube, or this is 1000 kg, but this is the. So if you have 1 gram of water and you convert it into steam at the same temperature at normal atmospheric pressure, means at a pressure of 10 raised to 5 pascals. The volume of stream formed is this 1671 centimeters. Latent heat of vaporization is this. It's asking about the change in internal pressure. Now I have some questions. During state change, what happens with the temperature? Temperature changes or remain constant? Marita.
Remains constant.
And if temperature remains constant, then internal energy should change or it should remain constant? Or it can change? Yes, it's an open question to all three of you. If temperature is constant, then what should happen with the internal energy? Internal energy should change. It can remain constant or it can change in some cases. See, for this question, you should always remember this result that we have written. See, I wrote that internal energy is kinetic and potential. Internal kinetic energy depends only on temperature, but internal potential can depend upon other factors. If you have an ideal gas, then internal potential is 0. But here, ideal gas is not given, you have water. So water will have both kinetic as well as internal potential energy. Temperature is not changing, so internal kinetic energy will not change, but internal potential energy. So just to confuse you, 0 could be an option. And if we put 0 as an option, then the chances the majority will choose this option, 0. Is it clear? This internal energy is changing. Which internal energy is changing? Kinetic or potential?
Potential.
Potential.
Now, to calculate internal energy, what you can do is use first law, which is delta Q, which is delta U plus delta eta. You can write that your delta U is its delta Q minus delta eta. Marita, how will you calculate delta Q? Yeah, how will you calculate this stuff?
Mass
Sorry?
into latent heat.
Yeah, mass into latent heat of vaporization. Perfect. Minus W. See, the pressure is constant. It's 1 into 10 raised to 5 pascals. Krishna, how will you calculate work done here?
P delta V.
Yeah, P into delta V, which is final volume, minus initial volume, which is equal to delta. So how much is the mass? Mass is 1 gram. How much is the latent heat? It's 2256 joule per gram. So it's already in per gram, so no need to convert it. Huh? So 2256 minus pressure. How much is pressure? It's 10 raised to 5 pascal. Then final volume, which is 1671. But see, your volume is in centimeter cube. So convert it in meter cube, multiply it with 10 raised to the power minus 6. Initial volume, which is 1 centimeter cube, 1 into 10 raised to the power minus 6 is equal to. So this is the change in internal. Note it down. Is it clear?
Yes, sir.
This is the first type of
Yes.
question on first law of thermodynamics. There is one more type of question which use PV diagram. Okay, good matter. So everyone have written up to here? Krishna, Adriel.
Yes, sir.
Okay, let's move on to the next question. Read this question. We'll do it together, but at least read the question.
So this is also from the NEET PYQ.
This is from the JEE, seventh question of JEE. Chapter Thermodynamics. So let's start with the calculation. So you are taking an ideal gas from A to B via two paths, ACB and AD. So which quantity will remain same in both the paths, in ACB and ADB? Which quantity will remain? Heat, change in internal energy, or work? See, its internal energy which depends only on the initial and final configuration of the system. So for both the path ACB and ADB, the initial and final is same. So for both the parts, the change in internal energy will be same. So for both the part ACB as well as ADB, the change in internal energy. You can say the change in internal energy for the path ACB is equal to change in internal energy for the second. Because internal energy depends only over the initial and the final configuration of the system. That is. Yes. So am I audible?
Yes, sir.
Screen is visible, huh?
Yes, sir.
Okay. Okay, Marita got the answer also. So delta W is delta Q minus delta U. How much is delta Q? When path ACB is used, 60 joule of heat flows into the system. The system is absorbing 60 joules, so that is 60. Or not, sorry, I should calculate delta. Delta U, which is delta W, and 30 joule of work is done by the system. Work done by the system means system is expanding, so it should be positive. So yours delta U comes out to be 30. Next is you can choose another path, which is A, B, B. If I choose this path, then you can say that delta U is again delta Q minus delta W. And delta Q will be U will be same as that of the path ACB. So how much is delta U? Delta U is 30 joule. The part we calculate the first part. Delta Q. This is what you have to calculate. Delta W is 10 joule. So your delta Q will be, it's 30 plus 10, which is equal. Ajit, tell me, is it clear?
Yes, sir.
Since in both the path, initial and final configuration is same, so what will be?
Sir, shouldn't we apply a sign convention in this formula?
I applied sign convention, see. When path ACB is used, 60 joule of heat flows into the system. Flows into the system, that means system is absorbing that heat, so it's positive. And 30 joule of work is done by the system. Huh? Whenever it says that work done by the system, that means system is expanding. If it is expanding, then it's 30. So it's 60 minus 30, 30. If I take another path, which is 80, sorry.
Work done by system is negative?
Yeah. No. Work done by system means system is expanding, it's positive. That is a confusion in physics and chemistry. In chemistry, work done by the system is negative, but in physics, work done by the system is expanding, so it's positive. The sign
Okay, sir.
convention of work done is opposite. In Priyadarshini, we started thermal yesterday, so from the next topic onwards, we'll start understanding what are we doing. We have started thermodynamics.
Okay, sir.
So the next topic is KTG. We'll start understanding KTG. And Krishna and Priyadarshini, you missed classes due to your exams. Now we'll provide you backup. Note it down. Krishna, Marita, written. Can I scroll it?
Done, sir.
Yes, sir.
So after first law of thermodynamics, no, we have to, we should study KTG before moving further. Because after first law, whatever we will do will need KTG. So we'll study KTG and then we will come back to thermodynamics. So we won't be doing complete KTG. We're doing topics of KTG that will be useful in thermodynamics. And after completing thermodynamics, we'll again come back to KTG and we'll do the remaining portion. So the first thing that you will need here is speed of gas. So if you have a gas, you take some gas in a container, then every molecule of gas will have different speeds. So when I say the speed of a gas, I mean average. So we can take various type of average. Three types of average are very popular here. One is most probable speed. The second is average. Third one is RMS. The first is most probable speed. So the most probable speed is root over 2 RT by M, where R is the gas constant. Capital M is the molar mass, means mass of 1 mole. T is the temperature. If you want, you can convert this in terms of mass of a single molecule. So when you convert this in terms of a mass of a simple molecule, it comes out to be 2 kT by small m, where K is Boltzmann constant. K is Boltzmann constant. And Boltzmann constant, usually it's written as K with a B in the subscript. And Boltzmann constant is gas constant divided by Avogadro. See, without KTG, you can't even attempt all questions of thermodynamics. Most of the questions of thermodynamics will be using some portion of KTG. And here small m is the mass of one molecule. So this is mass of 1 mole and this is mass of 1 mole. So if you want to relate them, capital M is Avogadro number multiplied by small. Next, what you can do is you can just convert this in terms of pressure and density also. You can write this as P by rho. See how we convert RT by M into P by rho? You should know this thing. PV, if I am writing for 1 mole, is equal to RT. Volume you can write as, see, density is mass by volume. So volume is mass by density. So instead of here, instead of RT, you can write PM by rho. So this is P, and M will get cancelled. That's why we get this expression. So you should remember the expression of speed for all, like for in the terms of temperature and molar mass, temperature and mass of one molecule, and pressure and density. Similarly, after most probable, you should be having the average speed. Average is root over 8 RT by pi. Or you can convert this in terms of one molecule, then it will be 8 R dot R. If you want to calculate in KT by pi into small m, or you can write this as root over 8 P pi by rho. And the third type of average, which is, by the way, most important, is the RMS. We can also calculate the RMS. RMS is root over 3 RT by M. Or you can write this as, this is root over 3 KT by small m, or which is root over 3 P by rho. Good. But then we'll do degree of freedom, and then we will see how we can connect it with the thermodynamics. So Priyadarshini, Krishna, this topic KTG is independent of thermal properties. So it is not connected to last lecture. From here, this is independent topic, KTG and then adiabatic process and isothermal process.
Done, sir.
Haji, written.
Done, sir.
Yes, sir.
The next is degree of freedom. In a very general sense, degree of freedom means number of independent coordinates. But here in kinetic theory of gases, we use degree of freedom in a very particular context, and that is degree of freedom means the number of ways in which your system can have kinetic energy. So degree of freedom means number of independent ways in which system can have kinetic energy. Possess kinetic. So the number of independent ways in which a system can possess kinetic energy is known as degree of freedom. So basically, through this degree of freedom, we try to calculate the internal energy of a gas. So there's a few things like if you have a gas, it can have three types of kinetic energies. The molecules can have translational kinetic energy, molecules can have rotational kinetic energy, or molecules can have vibrational kinetic energy. Vibrational type kinetic energy will come only at a very high temperature. At low temperature, you don't have vibrational kinetic energy. So at low temperature, you just have translational and rotational. So if you have a gas which is monoatomic, so let's write here the translational degree of freedom. Let's make a table here. So translational degree of freedom, rotational degree of freedom, vibrational. I'm not writing vibrational because vibrational will come only at a very high temperature. And this is total degree of freedom. So if you have a monoatomic gas can move in any direction, like it can go along x-axis, it can go along y-axis, it can go along z-axis. So molecules can have translational degree of freedom, which is 3. We say along X, along Y, along Z. A monoatomic gas cannot rotate. For rotation, you need a rigid body. So rotation is 0. So the total degree of freedom is 3. After monoatomic, if we take a diatomic gas, then in a diatomic gas, it can translate along X, Y, Z, any axis. It will have 3 translations. But it can rotate only about 2 axes. Means if you have a diatomic molecule, which is placed along X-axis, then this molecule can rotate along Y-axis. It can rotate about Z-axis, but it cannot rotate about X-axis, because about X-axis, the moment of inertia would be 0. So if you have a diatomic molecule, if it is placed along X-axis, that means it can rotate only along Y and Z-axis. If it is placed along Y-axis, then it can rotate only about X and Z-axis. So the rotation degree of freedom will be 2. The total degree of freedom will be 5. Similarly, if you have a triatomic molecule, and this is triatomic linear, means all 3 molecules are in same line, then it will have 3 in translation, 2 rotation, the total degree of freedom will be 5. But if you have a triatomic non-linear, means a molecule like this, it can have 3 translation and it can have 3 rotation. So the total degree of freedom will be 6. There's one more thing, at high temperature, diatomic molecule have 5 plus 2, which is 7 degree of. This extra 2 comes due to Y. It's not high temperature is not mentioned. So in 90% of questions, it's always translation and rotation. But if it is explicitly mentioned that your molecule is at high temperature, then add 2 more vibrational degree of freedom. Which usually the high temperature one comes. Note it down, then we'll see how we use this degree of freedom in calculating the kinetic energy of the gas.
Done, sir.
So can the high temperature case be applicable for the others?
Yeah, it's applicable even in triatomic. If you have high temperature, then you will add 3 more. But high temperature case is not possible in monoatomic. A single molecule cannot vibrate. For vibrate, we should have at least 1. After this degree of freedom, this is law of equipartition. Law of equipartition. The law of equipartition of energy says that energy associated with each degree of freedom for each molecule, you can say kinetic energy for each degree of freedom for each molecule is half Boltzmann constant into them. This is law of equipartition. Means if your monoatomic gas have 3 degrees of freedom, then the kinetic energy of that molecule will be 3 into half K. So if I write kinetic energy for F degree of freedom for each molecule is half into F into T. Or T just KB. So kinetic energy for F degree of freedom for 1 mole molecule is for 1 mole just multiplied with the Avogadro number. So F into Kb into T into Avogadro. So if I multiply this Boltzmann constant with the Avogadro number, how much is it? What is Kb into N? R. So this will be RT. This is for 1. So you can say this is your internal energy. Yeah? This is the internal energy of item. Internal energy.
So will we have F in the internal energy equation? Okay.
Yes. Internal energy of item. So why I'm saying this is the internal energy of an ideal gas only? Why not a real gas? Why I'm saying it's for an ideal gas? Why not for a real gas? At real,
Potential energy is 0.
yeah, because we are not including potential energy. Degree of freedom counts the kinetic energy. This is for right. So this internal energy, this expression of internal energy is the link between kinetic theory of gas and the thermodynamics and thermal properties. Just note it down. We'll see how we use this thing in thermodynamics. Why it's so important. So through this, we can connect thermal properties, KTG and thermodynamics. Have you written?
Yes, sir.
Yes, sir.
So let's go back to thermodynamics. So after first law of thermodynamics, the next thing is thermodynamic process. So a process can be isothermal, it could be adiabatic, it could be isobaric, it could be isochoric. So we'll start with the isochoric and isobaric process. So we'll start with the isochoric process. So isochoric process means process for which volume is constant. Okay, what does thermodynamic process means? When would you say that a thermodynamic process occurs? This also we discussed in the previous lecture. Thermodynamic process will occur when the thermodynamical parameters of the system will change. What are different thermodynamical parameters? It could be pressure, it could be volume, it could be temperature. These all are thermodynamic. If the thermodynamical parameters are changing, then we would say, okay, the system is in, there's some process that's occurring. So your process could be isochoric, your process could be isobaric, adiabatic, or isothermal. We start with the isochoric. Because maximum use of KTG is in isochoric and isobaric. Isochoric process. Isochoric process means volume is constant. So if volume is constant, that means change in volume is equal to 0. If change in volume is 0, that means work done is 0, because work done is nothing but change in volume. If volume is not changing, that means system is not doing any work, your work done will be 0. If we apply this thing to the first law of thermodynamics, first law of thermodynamics says delta Q is delta U plus W, work done. So if work done is 0, that means you can say delta Q is equal to delta U. Now see how we can introduce a specific heat and the concept of KTG. If I write this in differential form, I can write this as dQ is equal to D. This dQ can be written as in terms of specific heat. You can write this dQ as mc dt, which is equal to D. Where this C is the molar specific heat. Molar specific heat. This we did yesterday in thermal properties. Now, if I'm taking molar specific heat, then instead of mass, I'll be using number of moles, N mole. Number of moles. Now, the important thing is the specific heat of a gas depends upon the process. Means if your process is isothermal, then you're using specific heat for an isothermal process. If your process is adiabatic, then you'll be using specific heat for an adiabatic process. Here, the process is isochoric. We'll say molar specific heat at constant volume. You use this thing in chemistry also, and we will be putting a V here. So from here, if I do it for 1 mole, means N is equal to 1. You can write that your CV is CV dt is du. You can write that your CV is du over dt. So if you can differentiate your internal energy with respect to temperature, you will get C. And what was the formula of internal energy that we did in KTG? For 1 mole, what was the formula? Half degree of freedom into gas constant into temperature. So if I differentiate with respect to T, then I will be left with only its FR by 2. So this is CV, specific heat at constant volume. This is degree of freedom, gas constant divided by 2. This is how we calculate. After CV, so if you have CV, you can calculate heat, you can calculate many things. So that was about isochoric process. Now we can draw many graphs here. Usually 3 graphs are important. One is PV. If I take V here and I take P here. So Adriel, what should be the nature of the graph? PV graph for an just isochoric process?
Constant.
Constant. So what type of line will be here? Our line parallel
Linear.
to x-axis or y-axis?
So V is constant. So
So it's along y-axis. Let's draw a pressure temperature graph. Marita, what will be the nature of this graph, PT graph, for an isochoric process?
P will be directly related to T. So
PV equal to nRT. So you can say P is proportional to T and your graph will be a straight. Similarly, we can plot one more graph, and that is volume versus temperature. Priyadarshini, what will be the nature of this graph for isochoric process? Volume is not changing, volume is constant. Temperature is changing. What will be the nature of the graph? Krishna?
Parallel to x-axis.
Parallel. This is for an isochoric. After isochoric process, the next is isobaric process. Means constant pressure. For both the process, isochoric as well as isobaric, the most important thing is specific heat for those processes. I will not derive results. I just wanted to show you how we connect thermodynamics and thermal properties in adiabatic and KTG. So I will not derive results for isobaric. I'll just write them. So if you have an isobaric process means pressure is constant. So pressure is constant. There won't be any change in first law of thermodynamics. You can write this as this way only. It's PD. You will use Cp, which is known as specific heat. If you want to calculate heat, then you will write this as n number of moles Cp into delta. And what is Cp here? Cp is specific heat at constant pressure. Specific heat at constant pressure. To relate this Cp and Cv, you would use this Mayer's formula, Cp minus Cv is equal to R. Or we can say that Cp will be its R plus Cv. So you can write that Cp is R plus Cv. Cv we calculated in the previous section, that's Fr by 2. R plus Fr. So you can write that Cp is, you take R as common, it's 2 plus F divided. This is. Then you can calculate gamma also. What is gamma? Gamma is just the ratio of Cp and Cv. So if I take the ratio, then it comes out to be 2 plus F divided by 2. So see, if you know degree of freedom, you know Cv, specific heat at constant volume. If you know degree of freedom, you know Cp, you know this gamma. Gamma will be using in adiabatic process. Now let's plot the graph. PV graph, PV graph, PT graph. So this is pressure versus volume. Priyadarshini, what will be the shape of the graph? PV graph for an isobaric process? Krishna?
Parallel to
Shape of the graph. And this is PT. So this will be again parallel x-axis. If you have a VT graph, then they will be proportional to the graphs. Do it. We'll do questions over it. This was. So the syllabus for tomorrow's test is vectors, kinematics, FBD that we did, thermal properties, and the portion of thermodynamics that we can cover till now. Tell me once you have written this.
Done, sir.
So KTG will also be there for tomorrow's exam.
Yeah, this is also. So tomorrow's exam will be a proper exam based on your JEE pattern. So 20 MCQs, 10 integers for each subject, and out of those 10 integers, you have to attempt only.
So with negative markings, right?
Yeah, 20 credits. And the mock test, make an habit to just minimize your negative mark.
Sir, gamma is 2 plus f by f, right?
Yeah, 2 plus Fy, right, sorry. Two plus F.
Done, sir. Done, sir.
Written? Now see this question. So it's the last step here. The amount of heat needed to raise the temperature of 4 moles of a rigid diatomic gas from 0 to 50 degrees Celsius when no work is. So the heat required can be calculated as this way. NCTT. So Krishna, can you tell me what type of process is this? When no work done means, what type of process it's talking about? Isochoric, isobaric, isothermal, adiabatic, what type of
Isochoric.
process? Isochoric, why?
Because changing work done is 0.
Work done is 0, that means volume is not changing. So it's C. So you just have to calculate CV here. So for calculating CV, you will be using this expression FR by 2. For calculating F, we should know what type of gas is this. This is diatomic gas. So what is the value of F for a diatomic gas? Adil? Degree of freedom for a diatomic gas. Adil?
5.
5. So, and if in this question he mentioned that the diatomic gas is a very high temperature, then
7.
7. So if high temperature is not given, that means you don't have to count vibrational degree of freedom, it's fine. And how much is change in temperature? Change in temperature is from 0 to 50. So this is 50 degrees. So what are the number of moles? So here delta Q is N, which is 4. CB, which is 5. CB is 5. Multiplied by dt, which is 50. This gets cancelled out. So this is 500. This is the. Is it clear, everyone?
Yes, sir.
Okay, just note it
Yes,
down. We'll
sir.
do one more question. This question will be using the speed of gas also. So the question says,
Sir, is it not required to change it into Kelvin?
no, because change is same whether you take temperature in Celsius or you take temperature in Kelvin. The change in temperature is. So no need to convert it. If change of 50 degrees Celsius is equal to change of 50 Kelvin. So it does not matter when you have change. 14 gram of nitrogen is enclosed in a vessel at 27 degrees Celsius. So what type of gas is nitrogen? It's a monoatomic gas, diatomic gas,
Diatomic.
Diatomic.
diatomic. So degree of freedom, 5. how much work how much heat it's a very heavy. Be transferred. It's transferred to double the RMS speed. Double RMS speed. Calculate. Calculate your answer in joules. Huh? Good. Yes, molar mass is 28. Molar mass is 28. My dear, temperature is given, na? So just try to convert it into joules. Molar mass of nitrogen is given, it's 28. Temperature is given, write your answer in joules.
Okay, so I have to substitute for R as well.
Adrian, Manita, Krishna, are you solving? Or should I solve this numerically?
I'm solving, sir.
So you just have to first you have to calculate how much temperature you need to change to double the RMS speed. See, what the formula for the RMS speed? This is the formula for RMS speed, right? It's root over 3 RT by. So Adriel, if you want to double the RMS speed, what should be the temperature? How will you change the temperature?
So 2 into 2.
No, you will 4 times the temperature.
This is 4. Yeah.
So to double the RMS speed, your final temperature should be the double of the initial. Yes, Marita, you are close. Double the temperature. So the change in temperature will be 2T. No, not double, will 4 times. It's 4T minus T, which is 3T. So the change in temperature will be 3T. Next, you just need CV. How much is CV? That is FR by 2. So for a diatomic, this is 5R by 2. This delta Q. Delta Q is NCV into delta T. So how will you calculate the number of moles? Say you have 14 gram of nitrogen and it's 28 gram is the molar mass. So it's
So should we substitute the value of R?
yes, you have to substitute R and you have to put T into Kelvin now. So your T was 27 degrees Celsius, it would be 27. Not into plus 27. This is how you can calculate. So this is how they combine KTGs, PV, thermodynamics,